Hi, I'm Oded, an applied researcher in eBay for the last 5 years. In this session, I will talk about our framework for theme-driven recommendations. It was a great collaboration with my teammates. It includes Nazmul, Leandro, Yuri, Guy, and Yotam. Many eBay users turn to our platform to pursue theme-centric interests. These interests often come from diverse product categories. For example, a Chicago Bulls fan might treasure hunt autographed t-shirts, vintage posters, and trading cards, while a do-it-yourself enthusiast might explore power tools, hardware, and niche devices. Unlike transient shopping missions, theme-driven interests tend to persist over time and can be leveraged for personalization and serendipity. The problem is that current recommendation systems favor staying within the category boundaries. Let's consider a user that have viewed the Star Wars comic book on the left. Current recommendation systems will tend to recommend very similar items like additional Star Wars comic books, or they might go a bit broader and suggest additional comic books. What we usually don't see is more Star Wars related products that come from different categories. This is what we're trying to solve here. So for example, the recommendation module on the left, we identified that this user is a Star Wars fan, and therefore we collect different types of products all related to Star Wars. So how do we do that? In this talk, I'll present an end-to-end recommendation framework which is built on the user interest graph. This graph is generated by an LLM chain on which I'll talk now. I'll begin with the high-level overview of the chain architecture. To mitigate LLM latency, the pipeline is triggered. To mitigate LLM latency, the pipeline is executed in near real time. The pipeline is triggered upon processing a new user activity. The new activity is submitted to a Kafka queue, which activates the user interest graph generator, which is an LLM that generates the user graph. For our use case, we decompose the graph to paths representing user interests. And then these interests are ranked by a machine learning model. The top-ranked interests are passed into another LLM, which is called interest to recall, that generates query expansions. And these expansions are transformed into embeddings stored in the key value store for online availability. Now I'll break it down further, the whole process. I'll use a fictional user, Bob. Bob's eBay search history reveals quite a bit. He browsed this Star Wars wristwatch, and he looked at this creepy-looking Terminator watch. Also, he looked for a Van Gogh Pokemon card and checked a Star Wars poster, and finally, Dyson V15 vacuum. Great, so now how do we represent Bob's interests? We do it with the following graph. The top nodes represent broad passions, for example, sci-fi movies. As we go down in the graph, the interests become more specific. For example, the shopping mission for sci-fi watches. At the bottom, these are the leaves. The leaves are actually the search queries that were used as an input to generate this graph. The graph captures user preferences at multiple levels of granularity. Notice it enables traversing the graph to balance between relevance and serendipity. Each node in the graph has two properties. One is the interest names that you currently see, and also we have interest types, for example, genre or brand. These come from a fixed list and they add more structure because the interest names are freely generated by the LLM. Next, we rank Bob's interests. We trained a machine learning model to predict future engagement. We used user log data to build a dataset, splitting the last session from the earlier ones. The model then looks only at the first sessions and tries to predict whether the user will come back and engage with any of the interests. In this example, Bob re-engaged with the interest path, sci-fi movies, memorabilia, Star Wars, and therefore it is labeled as 1. Also, to encourage exploration across category boundaries, we applied sample weighting, placing greater emphasis on cases in which the predicted interest crossed into a new category. Now that we have Bob's top graph paths, we use another LLM for query expansion aimed at generating a varied set of products related to the interest. Each of these query expansion is transformed into embeddings using EBERT, which is a BERT model fine-tuned on eBay's data. And now finally, we are at the online setting, when a user actually enters the homepage. For item retrieval, we use the raw string query expansions via eBay's search engine to retrieve matching items, and also the embeddings using a k-nearest neighbors service. And then the recalled items, typically in the hundreds, are ranked by a deep learning model. We evaluated the framework via a 2-week A/B test in a homepage recommendation module, in which it competed with existing cross-category algorithm. Results showed a remarkable 17% uplift in the inspiration metric, clicks on categories never previously explored by the user. Also, we demonstrated gains in purchases and buyer counts. The results highlight that our approach effectively addresses theme-centric interest, but without compromising relevance. Also, we conducted offline evaluation, on which I'll talk a little bit. We used LLM as a judge. So given that each graph can contain dozens of nodes, and this is only a toy graph, that's not like the typical size, so we decomposed the graph into smaller subgraphs, smaller and more manageable subgraphs, and we passed each of these subgraphs to the LLM judge that was tasked with assessing subgraphs quality, detecting hallucinations, flagging unsafe recommendations, and evaluating task alignment. In conclusion, we presented an LLM-driven recommendation system that serves millions of users across billions of items. It includes LLM alongside collaborative filtering. Also, online A/B tests show improved engagement and discovery of novel content from previously unexplored categories. Thank you.
Why do we need an LLM to generate the user interest graph?
Yes, the key question. We experimented with quite a lot of designs. What we saw is that naturally user interests have this structure that you can build them as like these broad passions leading to more specific interests, and we found it valuable. We found that it enables us, as I said, to traverse the graph, so we can go to the down and be very close to the shopping missions, like the specific shopping mission, or like go higher, and then we're very close to the broad passions. And the LLM was tasked to generate it, like, again, the top nodes are, we said, like passion oriented, and these are like long living interests. And yeah, also it's how it's built. It's very different from the category tree. That was like another purpose of this graph, to be like an kind of an orthogonal taxonomy to the category tree, or the category, I mean like the product categories.